Our first question was, if we have a tube, plastic tube, whatever kind of a tube, with a cross-sectional area of 2 square centimeters, its length or depth is 2 meters. Okay, we got 2 meters of water filling the tube, and the tube is in a vertical position. Question is, how much, what's the weight of the water in the tube? You should pause and work this out unless you're just reviewing the class. But this is easily found. The volume of the tube is easily calculated to be 0.004 cubic meters. We're using the 2 square centimeter cross section and the 2 meter depth or height. The mass then is going to be the volume times the mass density of the water. Mass density of the water being 1,000 kilograms per cubic meter, something you need to know. And that comes out 4.4 kilograms, which then has a weight of 0.4 kilograms times acceleration of gravity, or 4 newtons. The next question is, how much force is required per unit of area to support that 4 newtons of water at the base? We imagine maybe I've got my thumb over the bottom of the tube. Maybe the tube has some kind of a base. In order to support the water, we've got to support with 4 newtons of force. Now, to get the force per unit of area, we divide the force by the area. We get 2 newtons per square meter, or 20,000 newtons per 2 newtons per square centimeter, 20,000 newtons per square meter. We call that a pressure. The unit of pressure is the Newton per square meter. We also call that Pascal. Newton per square centimeter is a perfectly valid pressure, equivalent to 20,000 newtons per square meter, or 20,000 Pascal. Next question. If the cross-sectional area instead of 2 square centimeters is 10 square centimeters, then how much force per unit area is required to support the column? And you should work that out. You can work it all out in exactly the same manner. The area is going to be 10 square centimeters here, which is going to give you 10 times the volume, 5 times the volume, because we have 10 square centimeters. 10 is 5 times 2 square centimeters. And so we're going to end up with 5 times the volume, 5 times the mass, 5 times the weight. Then the force per unit area, well, we're going to have 5 times the force because we have 5 times the weight, but of course we have 5 times the area, and if you work it all out, this is going to come out the same as before. It doesn't make any difference. From this, we sort of conclude that pressure is a function of how deep the tube is, or how deep the water is, not what the cross-sectional area or the area of the container happens to be. For the next question, we have this 2-meter column. We ask how much force is required to support the top 50 centimeters of that column. Okay, so 50 centimeters of column. Of course, you should pause and work this out yourself. Doesn't do you a lot of good just to observe it. Work it out yourself, then check it out. Okay, well, 50 centimeters, and this could be done in any number of ways. We could imitate exactly what we did before, only using a 50 centimeter depth. And we'd find that we have, in that case, 1/4 of the weight, because 50 centimeters is 1/4 of 2 meters. I've simply used that fact instead of doing all the details of the preceding calculation, but there's nothing wrong with doing those details. So for the 50 centimeter column, we have 1/4 the weight, and that implies, it turns out, 1/4 of the pressure. 50 centimeters being 1/4 of 2 meters, and you should be able to fill in the dots. If necessary, you can go through the entire calculation. The point here then is, we got this tube. We got 50 centimeters, we got some water down below that. The force to support the water above the 50 centimeter, or above this mark, which is 50 centimeters from the top, comes from whatever is here at the 50 centimeter level. Okay, what's here is the water. So the water at this level, the water right here, supports the weight above. Now you have 1/4 of the pressure, that would be 5,000 pascals. me write that in here in case you want to really check yourself. Okay. Okay, the water at this depth is under pressure 5,000 pascals, and that is sufficient to support all the water above. So that we think of the force that supports this weight of water is being exerted by the water right at this point, the upward force exerted by the surface of the water, even though it's not a surface, by an imaginary surface at this point.